Hello, today we will return to numerical methods for solving initial value problems. In the previous lecture we introduced and developed the Euler method, and along the way we have shown the ideas that we will be following, in particular the general setup. So here we go. We are given a first order explicit differential equation and also an initial condition. So with a bit of luck there is a solution passing through this point x0, y0, and we want to know this solution on a specific interval. But of course knowing the whole solution is impossible, so we choose a partition xi, equidistant partition of this interval, and at the points of this partition we want to find approximations of the values of the solution. That was the task. And to this end we developed the idea of a one-step method, which is a local method. It just looks at the situation at the specific point. We are sitting here and we want to move one step to the right. So changing x is very simple, it's just a shift. We make a step by h. And then we have to find the new value for y. And this could be difficult, this could be easy. So we wrapped it up in a symbolic notation. But for the Euler method, the formula was actually very simple. It's a linear function. We are moving along the tangent line to the solution. So it's a very nice multiplication, addition, very simple formula. And we will actually want to keep it for today. What we are going to change is the slope, because we were using the slope of the solution, which we found from the differential equation, by substituting the point x star, y star into the right-hand side. And there are some drawbacks. Let me just jot your memory. The Euler method lags behind development because it doesn't have up-to-date information. So we will definitely want to fix that. Where do we get inspiration? That's a good question, and there is an interesting viewpoint. Let's have a look again at what we are trying to achieve. Let's focus on one particular segment in our partition. So here is xi, here is xi plus 1, here is our solution, yx. And on this particular segment, we are trying to approximate this solution, and we are treating it as a new initial value problem. That's the whole idea of a local method. We start here at the point xi, yi, and we pretend that's a new problem. So there is some specific particular solution. And when I look at this solution must satisfy the differential equation and also initial condition, but this time with respect to xi, yi. Now, here is an interesting trick. I take this differential equation, and it's actually an equation which compares two functions with variable x, because of course the derivative has variable x, and also the function y, the solution, has variable x. So I can integrate on the left and on the right. Let's see. I integrate on the left, and I integrate on the right. And I integrate over this interval. So I'm starting at xi, and I finish at xi plus 1. What do I get on the left? Well, I'm integrating a derivative, so I can apply the fundamental theorem of calculus. And I get y at xi plus 1 minus y at xi is equal to, and there is this integral. Let me just symbolically write it down like that. Finally, y xi plus 1 is something that I'm looking for, because I'm sitting at this point and I'm trying to approximate the value of the solution at the next focal point. So I want this number, this number. Let me isolate it. Now, what is yxi? It's this value of the solution, and it's also the point where I'm sitting. So this is actually yi. And then there is this integral from xi to xi plus 1, fx yx dx. And that's the important formula that I wanted to see. And there is an interesting history behind it, and also this is natural in many applications, for instance in physics. But for us, the importance of this transformation lies in the fact that we actually know what to do with this integral on the right. Of course, we cannot integrate because we do not know the solution, so there is nothing to integrate. But we can apply the tricks from numerical integration, or quadrature if we want, to this particular integral. And because this is just one step in our overall problem, it makes sense to treat this as one panel in the numerical integration. So we have one panel here. We are trying to integrate over this segment, over this interval, and the simplest method that we know is the left rectangle method. So on the right, we get yi plus. And now we just take the left endpoint and substitute it inside, and that determines the height of this rectangle that we want to see here. So I put xi over here, and I get f xi, y xi. How much is y xi? The answer is this is yi. So that's something that I can determine because I'm sitting here at the point xi, yi, so I can take it and substitute it into my differential equation. So this is the elevation or the height of my rectangle, and then of course I have to multiply it by the width of this rectangle, which is the length of this interval, which is actually h over here. So by using the left rectangle method, I replace the integral with an expression like that, and this is no longer precise, so instead of the solution, we get an approximation. And what we have here is iterative formula, which is exactly the same as for the Euler method. This is the Euler method. We just developed it from this integral version of our differential equation, which is wonderful, another approach that leads to the same end. And what's more important, we made some error here, and it's a local error because we are just looking at one step in our approximation process. So this is a local error, and we know the local error for integration methods. We know the local error for the method of left rectangles. The error is O h squared. And this actually shows that the Euler method is a method of global order h, which means it's a method of order 1. So it all fits together very nicely. However, we want some other method. Well, left rectangle method over here leads to the Euler method. How about the right rectangle method? So again, instead of the actual solution, we will look for approximation. yi plus 1. Now, yi, that's the current elevation of our solution, the current value. And now, this integral is replaced by taking the right endpoint of the integrating range, or the upper limit of the integral, and substituting into f. So we are substituting xi plus 1, and then this has to be multiplied by the base of the rectangle. There is a little problem. First of all, we made an error when we are passing from integral to this right rectangle method. And this error is of the order OH squared. But we have to make another error because, let's have a look at it. In the integral, we are substituting xi plus 1, which is the next point in the partition. This we know. But then we substitute it into the solution that we do not know. But we can imagine that we are really successful or reasonably successful in our attempt to approximate this new value. And there will be some new approximation called yi plus 1, and we can therefore use it here, making another error. Now, it can be shown, and this takes a little bit of work, that this error, which we now made over here in this replacement, does not exceed in order the error OH squared. So this new line still generates a method of order OH squared, which is a local order. So globally, it's a method of order 1, just like the Euler method. Let's return to the general setup. So we are starting at point x0, y0, and then we use this formula to generate the next point at time in quotation marks x1, and then we use it to generate the next point, and so on. So let's have a look at the slide. We have an initial value problem, so we have a differential equation, and we consider it on some specific interval of length t, and we have the initial value. So that's the initial value problem. And also somebody gave us partition size. How many segments do we want to use? And then we find the step size h, just like in the previous lecture. Then we know how to start. We are starting at the given point x0, y0. That's this guy over here. And then we iteratively move to the right repeatedly. So that's the cycle where xi changes by shifting plus h to the right. And for the y value, we are using formula which hopefully fits. Yeah, it fits. Good. Now, there is an interesting comparison between the Euler method and this method. Well, the idea is almost the same. The formulas are almost the same. People also call it Euler method. And they call it the backwards Euler method. Why? Well, let's have a look at it. What kind of slope am I using? Because I'm really moving along a segment. Let's compare it. I'm sitting here. Let's say xi, yi. I've already done some work before. Okay, here is a solution that passes through this point. For the Euler method, I check on the slope here, and I use it to move to xi plus 1. And I move here. That's the Euler method. This new method uses slope, which I can find from the differential equation over here. F, that's the right-hand side. But I'm substituting the next point. So the backwards Euler method actually looks ahead, looks at the slope here, and uses it to move forward. So intuitively, we know that the Euler method lags behind, because when something happens to the solution, the Euler method learns about it only later on, only at the next stage, at the next step. On the other hand, this new method will be actually predictive. It will be proactive. It will react to developments already before they happen. It's a little bit complicated, actually, this interpretation. If you want to be really precise, it goes like that. We are moving above the time xi plus 1, looking for a new value yi plus 1. So we are looking at candidates. And at each point, you look at the slope here, and you ask whether it leads back to the original starting point. And if not, you don't want it. So we are moving up and down, looking for yi plus 1, which works in such a way that if you take the slope here, it will move you back. That's your right point, yi plus 1, over here. And a good question is whether such a point exists. And of course, we are getting here to the next name, or to the next word in the name of this method. It's also called implicit Euler method. I actually prefer the word implicit Euler method because it shows the substantial thing here. In the Euler method, which is also sometimes called forward Euler method to emphasize that we are going forward, you are sitting at a point xi, yi, and you just substitute it into the formula and you get the next guy. Over here, you are sitting at the point yi and xi, and you are substituting the next point in the formula which you do not know. So there's a vicious cycle here, but you treat it by looking at it as an equation. You simply solve it for yi plus 1. If you are lucky, you find a solution. If not, then you are in trouble, and you have to wait a few weeks until the chapter which is called Numerical Methods for Solving Ordinary Algebraic Equations. And that's a very good topic. There will be several lectures on it. So this method is actually quite difficult in implementation because at each cycle, when you are generating those new points, you have to keep solving algebraic equations. This can be really hard. So this implicit Euler method actually is of the same order as the straightforward Euler method, but it is harder to work out. So why would you want to use it? That's a good question. And the answer is that when we solve things numerically, there is always the order of the method, which is linear here, the global error. But there are also round-off errors in calculations when you do the calculations in a computer. So all these errors, they influence your answer. And we talked about numerical stability, that the methods have different sensitivity to these little errors. And that's exactly the point. The implicit Euler method tends to be less sensitive to those little round-off troubles. So generally, when you are trying to solve a differential equation, initial value problem, If this initial value problem is reasonable, then it makes sense to go with the Euler method because it's straightforward. You get explicit formula for the next point. Very nice. But if the differential equation is troublesome, then it makes sense to try something which is harder but more powerful. So these implicit methods, they are actually used in applications as a method of last resort. There are more implicit methods. This is just a simple representative. Let me show you an example. And we actually had this example before in the previous lecture because it's nice and we can see things. Y prime is equal to 1/2 y. Y at 0 is 1. That's the exponential growth. Now let's apply the implicit Euler method on some general interval, 0t, with some partition n, partition size, which leads to step size. Here we go. Now for the picture, I will actually look at interval 0, 5. Okay. The starting point is given. So x naught, y naught, given. In our case, x naught is 0 and y naught is 1. But I will show a general framework. How about the iterative step? So we are sitting at xi, yi, and we want the next generation. So xi plus 1 is obtained by shifting. We just move to the right by 1. And for yi plus 1, we are moving along a straight segment. The horizontal displacement is h, and the slope is obtained by taking the future point, xi plus 1, yi plus 1, and putting it into the right-hand side of my equation to obtain the slope. So I take this point, put it here, and I get 1/2 yi plus 1. And we have a nice implicit equation because the unknown is at 2 places. Now, in this example, for this particular differential equation, the situation is actually extremely nice because this can be solved for yi plus 1 algebraically. So how much is it? I have to isolate it. I move it to the left, factor out, divide. This is yi divided by 1 minus 1/2 h. And that's it. This is a nice explicit formula similar to one that we had for the Euler method, so we can just program a simple loop and fill in the points. Very nice. But we can also see that there may be some trouble. For instance, if the step size is 2, then we are really in big trouble. If the step size is more than 2, then the sign starts changing and the answers are totally off. So with those implicit methods, there are little troubles that one has to worry about. But for this simple example, this is actually no problem. I can handle it even explicitly using algebra that I know. But as I said, one would have to be really lucky because if this expression on the right is more complicated, it appears here, and I may be unable to solve this equation then. Okay, let's have a look at the performance. So, here we go. Interval 0, 5, step size 1, so the partition goes by 1. We are looking at values at integer points. The red circles, that's the forward Euler method. We actually saw a graph like that before in the previous lecture. But now there are little brown, let's say, diamonds. And you can see that they are getting ahead of the development. This is not really surprising. We talked about it. How about the performance? Let me decrease the step size a little bit. Let's say to 0.5. And we can see that the two solutions moved closer, and they seem to be moving at comparable rate. And this really confirms our expectation that these two methods are of the same order. So things work really nicely. Okay, let's have a look at this other interesting example, which is the logistic growth. Because in the logistic growth, we will nicely see illustration of the concepts of the comparison between the Euler method, the straightforward one, and the implicit Euler method. Okay, here we go. The solution starts, let's say, obliquely, 45 degrees roughly, and then it turns up. Now, the Euler method, the red circles, which are below, they react slowly, so the solution shoots up, and Euler notices only later on, oh, I have to go up. Whereas the implicit Euler, which is the brown diamonds, they see ahead that the solution is going to grow, so it starts growing up. too early, perhaps. Then when the solution turns to the right, the Euler method doesn't notice and keeps going up. And it ends up being above the solution. Whereas the proactive diamonds, implicit Euler, notices ahead of the time that the solution is going to level off, and levels off and drops below. So the two methods, the solutions, actually exchange places. Euler, implicit Euler, they go like that, and then they go like that. But they both focus and get close to the logistic growth. And if I decrease the step size, we should see improvement. Okay, yeah, we do. So much for the implicit Euler method. This is not the path that we will want to go, but it's a very interesting representative of a huge group of methods that we use only if we have to, essentially. Before we go to the methods or to the path that we really want to follow, here is an interesting idea. We are trying to use the integral version of our differential equation as an inspiration. And when we do, we arrive at an interesting situation. There's always the step size and some expression. Now, from the integration point of view, this expression is an attempt to determine the best height of approximating rectangle. And we have those higher order methods, and they differ in how they achieve the right height. But the same number, this expression, can be also seen as an attempt to get a good slope for our straight segment. Now, here is an idea that we would like to use segment, which is here on the right. Segment at a position that we do not know yet. And this creates troubles with implicit formulas. But there is an idea. I cannot really get to this place on the solution because I don't know the solution. But I have an approximation from the Euler method, which is a straightforward method, very easy to calculate. So this is something I'm getting almost for free. This Euler approximation. Why don't I use this Euler approximation to find a slope here, which is not the same as the slope here, of course, but with a bit of luck, they're almost the same. And then why don't I use this slope for moving forward, but from the original place? We always go from the original place. Okay? And that's a very strong idea, and I'm going to use it right away. Here we go. We are sitting here comfortably at the point xi, yi, and there is a solution passing through here, and this is the point that we want to reach. How do we get there? Well, let's try this integral form. Instead of the actual solution, we will go for an approximation. And instead of using first order methods, which is rectangle methods, we will go for something better. How about the trapezoid method? How does it work? Well, the height of the rectangle that we want to use is just an average of the height or the value of the integrating function in the left endpoint and the right endpoint. So we take xi and substitute. And we take the right endpoint of our integral and substitute. Okay, here we go. And of course we have to remember multiplying by h. Well. Again, we have a little trouble. First of all, this value is easy to achieve or obtain because what we have is actually yi over here. That's the point where we are sitting. And here we have the problem that we do not know the value of the solution at xi plus 1. So if we can somehow work it out, we will get a method of better order, namely of order 2, because that's the order of the trapezoid method. On the local level, passing to this approximation instead of integral, we made an error, OH cubed, of course. However, we have to work out this. We prefer to have explicit formulas. And the idea is, okay, I need to know essentially the slope, because this is the slope, that's the right-hand side of our differential equation. So I need to know the slope here on the right. Okay, here we go, the trick that I've been advertising. I take the slope here, let's call it K1, And using this slope, I will generate the Euler approximation of the value at the endpoint. But this is actually not the value that I want to use. This is just a temporary value. And traditionally, this is called y star I plus 1. That's a temporary value. And I use this location to figure out the slope. And then I use it as a slope on the right, as a replacement. So what I see here is f xi plus 1. And the value of the solution is replaced by the temporary estimate. 1, 2, 3, 4. Okay, that should be it. So this is the formula which I want to use, but you notice that I do not get yi plus 1 just as a formula. I have to make a preparatory step. I have to find this y star I plus 1 from the Euler formula. So this is actually yi plus fxi yi times h. The usual Euler business. Okay? Don't we have it somewhere here? Yeah, here. Euler method. So this actually goes in two stages. In the first stage, I find a slope here, which is called k1. Then I move along a straight segment in this direction using the slope k1. And after I take this new point, yi plus 1 star, and substitute it into f, I get something which I can call k2, because that's the slope here at the endpoint. So this is slope k2. And then I can actually see here the slope k1. And I can see that I'm averaging k1 and k2. Now comes a very special moment. I never use colored chalk because they are they are not easy to erase, and they do not really show well on videos anyway. But at this moment, I think it's time to use one. This is the only lecture in all my teaching career that I'm using colored chalks. So here at this position, there is a slope, which I'm going to call k2. And then when I want to make the final step of my method, the one that really counts, I take the slope k1, I take the slope k2, and I take the average. So the average I can see, let's say here, that's the average. We can call it k, and that's the slope that I'm using when I'm going for the true approximation, yi plus 1. Now let me make it prominent so that it stands out in the recording. Okay, so that's the geometric idea of this new method. We expect this new method to be of order h squared, global order h squared, that is quadratic method. Locally, we lost OH cubed when passing from integral to this place. And then we also lose something by passing to this approximation. And this is not so easy, but it can be figured out that this second error is also not serious. It's not serious enough to spoil the order 2 for this new method. Okay, here we go. Let's keep this in mind. Information from two places, and in this future place, I have to use estimate from Euler. This is the core of all the methods that will come today, this idea. Let's formalize it. This is called the Heun formula, but some people call it the improved Euler formula. Usually, these more advanced methods, they have many names. Different people call them in different ways. This is a little bit, let's say, unpleasant, but that's life. Heun formula seems to be, let's say, the one which is most widespread. Okay, the familiar setup, differential equation, partition, step size, and so on. X naught and Y naught are given, everything as we know it. Now it gets interesting. How do we pass to the next yi plus 1? First of all, we estimate the slope at the point xi. That's why I call k1 here. Yeah, exactly, k1. Then we use k1 to find estimate of yi plus 1 of this value, which is the yi plus 1 star. And when we have it, we use it to estimate the slope at the endpoint, k2. That's exactly this formula. So it all fits. And then finally, you combine these two slopes, k1 plus k2 divided by 2, that's the average, and use it as the slope for the official step. And here is confirmation. The Heun formula method is of order 2. By the way, this method is also a representative. It's a representative of a huge group of methods which are called predictor-corrector, because we predict the value yi plus 1 using Euler, but different methods may use different tricks. The idea is that you first predict how does it look like here, and you use this prediction to get more information, and with this information you then correct your prediction to a better one, hopefully. Okay? So that's a predictor-corrector method, the Heun formula. I'm not going to show you how it performs in our examples, because I'm going to introduce another method of order 2. Here we go. We are sitting at the point xi, yi. Here is our solution, and here is xi plus 1. We are trying to get to this place, essentially. What we have in store is the slope k1, which is over here. The tangent line at the point where we are sitting. Okay, there is another method of order 2 for estimating integrals, and that's the midpoint method. And I talked about it, it doesn't quite fit into the picture, into this Newton codes family, but it's also a method of order 2, and it's very popular because it's good. So, how does it work? To get this integral, we have to use elevation, or the value of function, at the middle of this interval. So the middle is over here, and in numerical analysis, this is actually, I think it's a mathematical joke, in fact, and I like it as a mathematical joke. This point is called xi plus 1/2. Of course, we never use fractions or decimal numbers in our indices. We always use integers. So this is really like a mathematical joke. This is not quite correct, but it sends exactly the right message. xi plus 1 means I made one step to the right. xi plus 1/2 means I made half a step to the right. The comparison of formulas is obvious. xi plus 1 is xi plus h. xi plus 1/2 is xi plus 1/2 h. Okay? So what I would like to do, I would like to use information from this slope. That's the idea behind the midpoint method. Because, let's have a look at the exponential growth. Here the slope underestimates. Here the slope overestimates. If I look in the middle, it would seem that the slope is exactly the right one, more or less. Okay? So it makes sense to ask, what is the slope here, and then use it. Well, how do I get this information? I'm in a similar situation. Here I was trying to find a slope at the end, and I used a temporary point to get at least an approximation of the slope. I will use the same trick here. I'm sitting at the point xi, yi. I know the slope k1, and I can move forward. And I can move by half the step. That's the idea. So what I'm going to use a temporary point yi plus 1/2 with star, which is yi plus, and now I have to be careful, this is the slope, and this is half a step. Okay? We always have to put displacement here in the formula, horizontal displacement. So if I'm moving here by half a step, then also here I have to move by half a step, otherwise the data is not consistent, otherwise it's nonsense. So this is another thing we will have to focus on when we are developing more powerful ideas. Okay? So I move half a step to the right with x, I move half a step to the right along the corresponding segment, and I end up here. This is y star I plus 1/2, and I check on the slope at this place. And again, here comes the moment for colored chalk. So what could be the slope here? Let's say this one. So I will call this slope k2, and I didn't quite manage, so let me use the chalk advantage. I can cheat it a little bit like that. Now it looks like a straight line, more or less. So let's say that I found this slope. Well, do I feel the need to combine it with any other information? Actually not. I think that the slope in the middle is exactly what I'm looking for. So I use it, and again, we always start from this initial point. From this initial point, now I move in a parallel way. So I move like that, and I go all the way to the end. This will be actually the official yi plus 1. Parallel movement. Okay? That's the idea behind a competitor to the Heun method. The competitor looks in the middle and uses this slope. So the slope K2 I obtain by substituting this approximated middle point into f, into the right-hand side of my differential equation, and then I use it. Sorry, h here. So as you can see, the formula always looks the same. There is always some slope, exactly as I promised when I was introducing today's lecture. Okay, another slide coming up. Many names. Midpoint, which is actually a good name because it describes the idea. So when you describe the idea in the name, people generally narrow it down fairly easily. Modified Euler formula, improved polygon, many names. RK2, that's a good name also. I think that's the, let's say, most widespread name is RK2 for this method. And why RK2, we will see soon. Okay? The algorithm does exactly what I put here. So we estimate the slope K1, that's the slope at the initial point, use it to move just half away, and the formula fits. You can notice this 1/2 when we are moving x corresponds to 1/2 when we are moving y. I talked about it because of consistency. Then we estimate the slope at the midpoint and we use it. Okay, the midpoint method is of order 2. So what we have here is 2 methods of order 2, and again you may ask why 2 methods. And the answer is numerical methods play favorites. For every method, there are some problems that they really hit it off with, and they provide superior answers, superior results. Sometimes it may happen that you take a differential equation, apply a method of order 2, and you start getting results like from method of order 3 even. So there is definitely this situation that different methods have different favorites, so it makes sense to have more methods. In general, the midpoint method is considered a little bit better regarding the influence of numerical errors, essentially. So again, it boils down to stability. So when you have a typical differential equation where the right-hand side is reasonably smooth, then people slightly prefer the midpoint method. But there are also differential equations, very nice, where the Heun method is actually better. So yeah, at least you have a choice. That's nice to have a choice. Okay, now we have 2 methods of order 2, and it makes sense to look at some performance. Here we go. Here we go. What we can see is red circles, that's the Euler method. We can see the brown diamonds on the top, that's the implicit Euler method. And then we can see, well, it looks like the aiming cross, but it's actually a little blue square and the red cross. These are marks for the Heun method and the midpoint method, which actually doesn't really matter because they are identical. For the exponential growth, they yield the same answers. And they seem to be better because those marks are closer to the actual solution in blue, but we already should know that this does not mean much because this is just one instance, and it may easily happen that a worse method for one particular solution shows better answers. The substance of order, of higher order, is in better improvement. So let's decrease the step size and see what happens. So from 1, we go to 0.5. And we can see that the methods of order 2 are almost on the solution, while the methods of order 1 are still a little bit away. How about 0.01? 0.1. Here we go. And the marks for the methods of order 2, they are actually right on the solution. So they seem to work better. Very nice. Let's have a look at the logistic growth. For the logistic growth, We have, again, red circles and brown diamonds, and we saw it today already. They go like that. What's more interesting is the crosses. Now there is a difference. Let's see who's better. The crosses seem to be closer to the solution, and the crosses are the midpoint method. So for logistic growth, the midpoint method seems to be a bit better. It follows the solution closer, while the blue squares, they are a little bit farther away. What's interesting, as we move behind the band, then actually the methods of order 1 seem to be better. As I said, this may happen. That's why it's dangerous to make judgment just from one picture. So generally, it is better to try and check, okay, can I enlarge it still farther? I think this picture deserves it. Yeah. Now we can see a little bit better. We can see the difference. So the closest to the actual solution is the methods of order 1 here on the right. But let me pass to a smaller step size. And now it is getting really messy. Okay, here in this initial part, the methods of order 2, they are better. But what's happening over there? Let me try a little trick. I will put k minus 1 and k plus 1 here. This could be it. Okay, so enlarge it. Perhaps, okay, I will shoot it 0.5. This could work better. And minus 0.5. Let me focus just on this segment on the right, and perhaps let me look at it a little bit more. So I will add plus 2 here, and I will add plus 4 here. So we will just focus on this part after the band, and we can see that now the methods of order 2 are actually closer. Well, this is questionable. The Heun method is still the farthest one. The midpoint method is now as good as the implicit Euler. So let's pass to a still smaller step size. Let's say 0.5. And again, I will focus a little bit more on the graph. I hope I didn't yeah. And now finally we can see that the methods of order 2 are closer. See, that's the idea of a method of higher order. Initially, for larger steps, those methods, midpoint, Heun, were actually worse. But with smaller and smaller step size, they are suddenly ahead. They are better. Just out of curiosity, let's try 0.1. That's a good step size. Well. I guess I will have to focus really closely to see any difference. And I can see over here that really the methods of order 2 are right on the solution, while the Euler methods, implicit and the explicit one, they are still far away. Relatively, because I'm really focusing closely around the graph. So that's a good story to see. We could really see how the methods of higher order initially lag behind, but they get ahead. Okay, let's try to make some general conclusion from this picture. The topic for today is Runge-Kutta methods, and we can see it exactly here. You are sitting at a specific point, and you want to find the best possible slope. How do you do it? You are simply getting information. You are checking, okay, what's happening here? What's happening here? What's happening here? Now, when you have this information about slopes, or rather approximate slopes at different places, you can combine it and make another foray forward. For instance, here you have the slope in the middle, so why don't you go again using this slope just half the way and try to get a better approximation of the slope in the middle? Is it possible? Of course, yes. And you can do it 5 times. So you go in the middle, get a slope. Use it to go in the middle, get a better slope. Use it to get in the middle, get a better slope. After you do it 5 times, you say, okay, I like this slope enough. And you make the final step. So this is the idea of Runge-Kutta methods. You make several journeys forward, and you can go by the whole step, by a half a step, by a third step, 3/4 step. You can do all kinds of things. And then you combine the information. At each step, you're allowed to use information that you already have, the temporary information. So you can develop very complicated procedures. And of course, you are aiming to set them up in such a way that the more work you do, the better answer you get. So generally, the more data you have, the higher order you want to see. For the Euler method, you had one piece of data, K1, and we got a method of order 1. With these two guys, we had 2 slopes, K1, K2, K1, K2, and we got a method of order 2. So this looks very good. Let's have a look at a general definition. Okay, here we go. The substance of every Runge-Kutta method can be captured by this triangular scheme over there. This is called Bachelor table. Actually, in books, they call it Bachelor tableau. Okay, I'm not going to embarrass myself by trying to pronounce it, okay? So it's a table, Bachelor table. To understand it, we have to look down here at those lines which are disappearing. So we will scroll a little bit. Let's try to develop this whatever table for our two methods. So how does a typical Runge-Kutta method go? It starts with information that we have. We have information xi, yi. We put it into the right-hand side. We get slope k1. That's exactly it. So we have no other choice. That's why it's not in the table. It's actually this 0 here, if you want. We have 0 choice at this moment. Okay, what's next? K2. K2 is the next slope that we want to see. And we are sounding to the right somewhere. And how far do we go? Well, this is something that can be recognized by checking on x. Because you look how the x changes, and that says all. So I can see xi plus c2h. So c2, that's a constant which tells me the proportion of the step. For the Heun method, we went the whole step forward, so the proportion is 1. That's xi plus 1, the whole step forward. For the midpoint method, we went by a half. And then we also have to change y, and there is a constant a21. Now, I talked about it. When you go by a segment, by a straight line, the change in x and y must be proportional. So this a21 should be actually the same as c2. So in the first row, in the first meaningful row in our table, the number on the left and number on the right must agree. Now it gets more interesting. Once we have this slope, k2, in place, we can use it to again get another piece of information. So let's have a look at the next line, k3. We move to the right, and c3 tells us the proportion. Now there is no attempt to find k3, so actually for these two methods, that's it. But let's imagine that we make another journey. So C3 tells us how far we go along this segment. 1 means we go all the way, half the way, 1/3, and so on. Now, how does the y change? Now, in the y, we want to see C3 again, but we can also see that we are combining the two known slopes. So there's actually two things happening. First of all, we take the slope k1 and k2 and take the average. It can be weighted average. So for instance, okay, let me see over here. For instance, I can take 1/3 of k1 plus 2/3 of k2. So it depends how much I trust these two slopes. In my picture, it seems that I trust slope k2 twice as much as I trust slope k1. So these weights, they give you a chance to distribute your trust. And the important thing is that for average, the summation of these indices must be 1. Otherwise, it doesn't work as an average. But then you are making a step to the right with proportion C3. So after you find the slope that you like, this is the slope, the new k, you have to multiply it by C3, by the proportion and the step size. So what they do in this theory, they take your weights and they multiply them by C3 and they call them A32, A31. Okay? So this is actually harder to see what's happening because it would make more sense to see C3 factored out. But this is for some historical reasons. People stick with this form. So let's stick with it too. What we see right away is that when I sum up those AIs, because they are just multiplied out, that they should give me C3. So in the second meaningful row, A31 plus A32 must give C3. And then they keep going like that. Now we have 3 slopes, so we can combine them, make another trip to the right. And after we do it n times, we have n slopes, and we decide to combine them. And we make an average, slope k, that's the official slope that I want to use. And again, it's a weighted average. I'm weighting those temporary slopes that I have according to the way I trust them. And then finally, I use the slope. Okay? So the weights W, they are in the lower row of the table, and again, they should sum up to 1. Now, in my case, for the Heun method, I had 2 slopes, and I trusted them equally. So I was using 1/2 and 1/2. You can see it over here. 1/2, 1/2. That's the weights. For the midpoint method, I didn't care about slope 1. I really trusted only slope 2. So that would be the chart for the midpoint method. Okay? Now, the trick is that you can try to develop those coefficients C, AI, and so on in different ways, because the conditions that the rows must sum up and so on, they are very, let's say, lenient. There are many possible ways to arrange methods of a specific order. And you want to create a table in such a way that the method that you obtain is of exactly the same order as is the number of slopes, in this case, capital N. And this can be done for any order. And as I said, there are many ways to try it. So there are many competing, let's say, methods. And generally in applications, people found out that what works best is the method of order 4 and a specific one. There is a very special method of order 4, and it's called RK4. By the way, now you understand why this method is very often called RK2, because it's the most popular method of order 2 of this type, Runge-Kutta method of order 2. Let's have a look at this method of order 4, and we will need some room. Okay, here we go. We are sitting at the point xi, yi, and we decide to move 1 step to the right by h using RK4, which is the default Runge-Kutta method of order 4. There is no confusion this time. Everybody calls it RK4. Everybody knows what it means when they know numerical analysis. Okay, here we go. How does it work? First step, we want to estimate slope K1, which is exactly based on the point that we are sitting at. So we can see the slope K1 over here. And the question is, how far do we want to go? And the answer is, well, we want to take this slope, which is part B, and use it to go half the way. We can see it here. It says estimate y at a half step, xi plus 1/2 h. So here is the half step, xi plus 1/2, which is xi plus 1/2 h. And we go all the way here, and this will be temporary y star I plus 1/2. That's what we see in the first line of part B. We are using slope K1, going half the way. And when we are there, we use this information about this location to estimate slope K2. K2 is taken half a step using this temporary y. So, here we go. Red curve. What could the slope here be? This one, but not quite, because we moved away. Let's say this one. So this could be the slope K2. And now, we keep starting from this original location. So now we are going to follow slope K2 to find some information about slope K3 at a specific point. So that's step C. Okay, how far do we go along this slope? Again, half a step. We want to improve the estimate at half the step. So we are going using the slope K2, and we obtain y with 2 stars. Okay, parallel, parallel. I hope this is parallel. We go half the way. So I will show some parallel marks here. And this place is y star star I plus 1/2. Okay. So far, so good. Now, let's go for D. Let's have a look at the end of the first line in the step D. Which slope are we using? We are using slope K3. And we see the slope K3 at the end of step C. Okay? At the end of step C, we determine the slope K3 using this new midpoint. Okay, now we are fairly close. So I think the slope could be somehow like that. And again, let me make it really prominent so that you can see this. This is the slope K3. And using the slope K3, we are moving in step D. okay, we are moving the whole step. So there is an interesting thing. Notice that we never mixed the slopes yet. All the steps were made using a specific slope, not any combination, any weighted average. So we are moving using slope K3 by the full step all the way to the right. Okay, slope 3, where perhaps I was a little bit overgenerous. Well, we will see. Step 3, we are moving here the whole way up to here, and what we have here is yi plus 1, but a temporary one. And again, this direction is parallel to this direction. And what we obtain at the end is another slope, yet another color. I would think that the slope here could be like that. This is K4, and the color is not quite okay because it seems similar to yellow. I've been hoping for more difference. Okay, so we have 4 slopes, because that's D. Part D, we are getting slope K4 at this new point. And finally, we make a step forward, the official one, where the slope K is taken as a weighted average, because we are dividing by 6, and summing up, and the coefficients also give 6. So perhaps I can write it like that. The official slope for this method is 1 over 6, the slope K1, plus 2 over 6, slope K2, plus 2 over 6, slope K3, plus 1 over 6, slope K4. And that's it. And we are getting method of order 4. 4 pieces of information for slopes, method of order 4. It fits nicely. Before we look at the performance, remember, inspiration from integration. What is really happening here? I am taking 1/6 information at the left endpoint, that's K1. I am taking 1/6 information at the right endpoint, that's K4. And here, K2 and K3 are both information at the midpoint. So actually, the midpoint has weight 4 over 6. 1, 4, 1, 4, 1. These are exactly the weights for the Simpson method. So if you want to approximate this panel using the Simpson method, we would be distributing weights 1, 4, 1, but we actually decided to take this middle information and obtain it twice to improve our chances. Simpson method is for the 4, RK4 method is for the 4. It all fits together, okay? And that's it for the RK4 method, and essentially that's also it for the Runge-Kutta methods, because it doesn't get any better than this. This is the best general purpose Runge-Kutta method. And this was also the last moment this year that I'm using the colored chalk, and I'm glad, because now my fingers are also colored, and that's why the white chalk is also colored. They spread like a plague. Okay, let's go to see some performance of the RK4 method, which I've been praising really a lot. So let's see. Here we go, the exponential growth. We have seen the majority of this picture before. The Euler methods, red circles, brown diamonds. Not all that great. Or the 2 methods. They've been here, the Heun method, the midpoint method. That's the funny aiming device, which is quite close to the actual solution, but not all the way there. And finally, RK4 method, the black circles, and they are right on the money. It doesn't get any better than this. So the exponential growth is really nice for RK4 method. It shines here. I could show a similar picture for the logistic growth, and it will also look great. So let's talk about something, let's say, slightly more challenging. We didn't spend much time on numerical stability. Actually, the notion of stability is tweaked depending on what people need. And for the differential equations, there is this combined effect of the local error of the method and numerical errors in calculations. And they can be very unpleasant. We always work on a specific interval, and there we try to approximate. But for practical purposes, it sometimes makes sense to go farther. And moreover, when you try to go farther, it tells you something about the quality of the method. So there is a special notion of stability for differential equations, and it goes like that. You test stability of a method by taking differential equation, or rather an initial value problem, where the solution is bounded. So for instance, the solution looks like this. Bounded means it's within some strip. And then you take your method, you pick some step size, h, you apply it, and you see what happens. And for a method to be stable, you always to see the numerical solution to be also bounded when you go indefinitely. So there must be some strip, perhaps wider than this one, perhaps this strip, so that the numerical solution stays in this wider strip all the time. It never strays, it never blows up to infinity. That's the idea. So stable methods for differential equations are very useful, but they are really hard to get. For instance, the Runge-Kutta methods, they are not really stable. Let's have a look at a simple example. We had an exponential growth, which looked like this. This is a slightly modified exponential growth. It's based on the function 1 plus c times e to x squared. And we saw this as an example several times. What I'm going to do, I'm going to introduce minus here, which also appears here. These solutions are all bounded. In fact, they look like this. There is a horizontal asymptote, which is also a stationary solution, by the way, at level 1. And depending on c, you may be approaching this stationary solution like that, or perhaps like that. So they're all bounded. Let's apply our methods to this differential equation and a specific initial condition. Here we go. So I will read the problem. You can see that the differential equation agrees with this one. The initial value is 3, so we'll be approaching this asymptote from above. And now let's see how the methods perform. We see the solution, very nice. And let's have a look at the red circles, which is the Euler method. It goes first to the right because it doesn't catch up to this quick bending downwards. Then it goes down, overshoots, and levels off, and goes with the solution. So Euler method works really well. Implicit Euler does it the other way around. Proactive, proactive, and then goes along the solution. Blue squares, that's the Heun method. Red crosses, that's the midpoint method. Two methods of order 2, and they are a little bit comparable, but different. The Heun method is worse a little bit. I talked about it. The midpoint method generally has a better chance of working reasonably well, but both of them actually depart and go to infinity. So this is definitely not stability. The Runge-Kutta method of order 4 is the black circles, and they are better at following, but eventually they also depart. Now we can look a little bit more to the right, and we will see that even the Runge-Kutta method of order 4 really goes away, and goes away quickly. It disappears very fast. We do not see it on the right. So these Runge-Kutta methods, they are not stable because they are not bounded. The outputs are not bounded. This is really bad. But they are conditionally stable for this particular differential equation, which means that if you make the step size small enough, things will become better. So let's have a look at a smaller step size. How about 0.1? Well, with step size 0.1, all the solutions seem to be following the actual solution nicely. So let's just have a look more to the right, because we want to be sure. So let's go all the way to 16 in our picture. And it seems that, yes, once we make the step size 0.1, there is no problem with disappearance to infinity. So for this particular example, for this particular initial value problem, these Runge-Kutta methods are conditionally stable. And that's typical. Of course, one has to be really careful. This is an introductory course, but when one starts applying Runge-Kutta methods to serious problems, one has to worry about this type of stability. An analysis has to be made, things like that. So we will not go into it really in this introductory course. But this all begs a question. Normally, we do not know the solution. So how do we judge the quality of the output? Here is a typical example. I have a differential equation here, and when you look at it, it's not really crazy. Derivative, y derivative is equal cosine x, y squared. That's a nice differential equation. It exists everywhere, the right-hand side. It doesn't have any restrictions. So let's apply our favorite methods. And this is the output of the Euler method. We got a bunch of points. Now, what do we think about them? Is it good or not? Well, let me add the solution, because I know it, by the way. So where do I see it? Output, both. Graph. Here we go. The blue curve, that's the actual solution. It's periodic. And you can see that the Euler method is failing quite badly. So how do I learn about things like that if I do not know the solution? And that's a key question. I've been talking about it in the previous lecture a little bit, and I delayed the answer. Now is the time to look at it. We will need a lot of room. We already asked the error question before when we were talking about numerical differentiation and the numerical integration. And we met the idea of Richardson extrapolation and the corresponding error estimate. It worked like this. There is some quantity that I want to approximate, and I produce, using some method, an approximation which uses step h. And I'm interested in this error. To obtain it, we need some data. So we make another approximation using the same method, the same settings, but with step 2h. So most likely it will be less good. And there was a formula which we had on the slide. Everything is ready for us. However, we cannot just apply it to our situation here because it's different. Let's have a look at it. We have an interval x0 plus t, and there is some solution floating around that we want to approximate. So we choose a step size, we choose some method, and we apply it. Let's say the step size corresponds to partition size 6, so that it's a nice picture. So I split this into 6 parts. Here is the step size h, and for each location I get an approximation. And let's say that it's a fairly good approximation, so it could be like that. So this approximation will be called Zj, and it corresponds to step h. Then we need a second attempt using the same method with step 2h. And this one I will call yi. Now you may say, hey, wait a second, why there is a different index? And the answer is that when we double the step size, we are actually not going by chunks of this size, but by chunks of this size. That's the size of our step now. So we never get here. We start over here with y's, and the next guy appears here, and it's most likely a less good approximation. And the next guy is over here, and the next guy is over here. These are the y's. So they are not only less good, but they're also more rare, so to speak. Now the problem is that for the Richardson extrapolation, you need to have a pair of values. And we only have pairs at these locations. So we can get error approximations here, and here, and here. And this means that for the solutions at j, the one which is better, we actually cannot get error estimates because these guys, they don't have a partner. So we are forced by asking for the error estimate of the solution which we actually like less. That's life. So we are going to estimate the error for yi. Let's have a look at the situation. Here is the solution at xi. Here is our attempt, which is most likely worse, yi. And to get the data, we look at the solution z, the better one. But now we have to be careful, because this is y1, and it's not paired with z1. It's paired with z2. So y1, z2. Here is y2 and z4. And it keeps going like that. The index for the z solution is always double of the index for the y solution. So yi is compared with z2i. And the error that we want to know is this one. So you can see that the situation is actually different. We cannot just use the formula from the Richardson extrapolation. We have to use the idea and work it out. If this is the error for the solution yi with step 2h, what happens if we halve the step? Well, we have to assume that this method which we used has order p. And then when we take half a step, the original error decreases, it gets divided by 2 to p. That's the idea of order. So, in this picture now, we have all the data. Let's put them together. This distance, how much is it? Well, that's actually z to I minus yi. But it's also e minus 1 over 2 to p e. And that's an equation that we can solve easily for the error. It's actual error for yi. Okay, factor out, use common denominator, put it here. 2 to p divided by 2 to p minus 1 times z to I minus yi. That's the approximation of the error. And then we put it into absolute value, of course, because we are just interested in the magnitude. We take maximum, and we get approximation for the global error. Okay? So this can actually work out rather nicely for the Richardson idea. It also works for the differential equations methods, but we have to be careful because we are actually now working with the worst attempt. Does it work? Well, let's test it. Over here, what we see is an attempt to solve a differential equation using the Euler method. So the order p is 1. And when we look at this approximation of those circles, we can see that there is a little bit like a periodicity to the error. Because in those bands down here, in the valleys, the error is smaller. But when the peak comes, the error shoots up. Error is very large. So now when I look at a picture of the error, it should also look peaky. We will see. Step size 0.5, that's the usual step size for our pictures. So the red curve, that's the actual error. And it is sort of like periodic. And the green curve, that's the Richardson approximation of the error. And it, well, okay, it's not all that great, is it? But that's because step size is 0.5. Now, if we try a smaller step size, things should improve. Let's have a look at it. 0.1. Bang. Well, it is a little bit better, especially in those lower areas, lower sections. But in those peaks, the error estimate is still not close enough. So I have to go to, let's say, 0.01. And it will take time because now there is a very tiny step size, so there are many, many points to calculate. And the two curves are now quite similar. Well, there's still a little bit of a difference over there in those peaks. So this is not really great, but that's because this is a very good differential equation. I actually chose it intentionally to sort of work out these methods really hard. Of course, we know that this kind of reasoning always works better if the order is better. So what I'm going to do, I will go back to step 0.5 and show it so that we can keep it in our memory. Let's have a look at this green curve. It's like half the way. It's half the height of the red peak. So this is the Euler method with step 0.5. And now I will change it into, let's say, the midpoint method, which is of order 2. Okay. So I expect that for a method of higher order, the approximation of the error will be better. Bang. Well, it is better. The red curve, that's the actual error, and the green curve, that's the approximation. And even with step size 0.5, this is already quite good. So the Richardson estimate actually seems to work really well. Let's have a look at another interesting comparison. We will now look at the local error. So we will start somewhere, let's say over here, and we make just one step. One step of the local method, of the Euler method, and so on. And then we will compare with the Richardson estimate. So to get this local estimate, we are sitting here. We make one step with our method, yi. And then for comparison, we have to make two steps with the method z. And step is h, h, 2h. And because it's such a simple situation, just one step, the errors will be just numbers, we can actually do this for many steps and draw a graph. So that's a local situation. Here we go. We use Euler method again. So the red curve is the error of one step, local error, at a specific location, as it depends on the step size. And the green curve is the Richardson estimate. And we can see that the Richardson estimate for smaller step sizes works really, really well. Actually, the fact that the green curve is getting closer to the red curve does not mean much, because for error estimates, we always worry about the relative error. So what we worry about is the proportion, the distance between the green and the red curve compared to the actual value of the error. And the fact that the distance is getting smaller does not really mean much, because the error itself is also getting smaller. So the ratio, the mutual ratio of the difference and of the red error, that's of interest. So what I'm going to do, I'm going to focus on smaller step sizes, and we will see whether the curves, when they are enlarged, when they are scaled, are still that far away, or perhaps they are closer. So we'll be interested in the upper right corner, but we will now look at smaller step sizes. So here we go. A little focus, a little zoom. And when we zoom in, we can see in the upper right corner that the red error and the green approximation are almost the same. The distance, the difference is now negligible. So this really shows that for smaller step sizes, the Richardson estimate works really well. However, it's not actually used in applications very much. Let me put it this way. It can be used, but people prefer a different approach, and I will talk about reasons shortly. So what is the other approach? Well, it goes like that. Here is the interval and the solution that we are trying to approximate. Okay, we are not really interested in the solution. We are interested in the approximation that you want to see. Let's call it yi. Now there is step h, and this was obtained using some method of order p. And we want to get an estimate for the error, which precisely is the precise value of the solution minus the approximate value of the solution. Now here's the trick. This other approach uses so-called control method. So I will use a different method which produces approximation with the same step. So for Richardson, I'm changing the step. For control method, I'm keeping the step, but I'm using a method of different order, which is larger than p. And I get new approximations called zi. Because I'm using the same step, then these approximations, yi's and zi's, they actually share locations. So I have pairs everywhere. This is the first advantage of this approach. I don't have to worry about things like that. And what I'm going to do, I'm going to take and replace the solution by its approximation using the better method. Now you may say, okay, wait a second. When you change the solution for approximation, you are introducing another error. Isn't it bad? And the answer is, well, actually not, and that's why I'm not going to replace it. I'm going to use a different trick. I will keep the solution, and I will subtract zi and add zi and subtract yi. It's still the same. I didn't do any cheating. This is proper mathematics. But now let's have a look at it. This is the error of the method yi. Because it's a method of order p, this is some expression which disappears at the rate h to p. On the other hand, this group is the error of the method of order q, because it's the error of zi, of the approximation zi. So this expression disappears at the rate h to power q, which is higher or larger than h to p, higher power. Now, when h is near 0, then h to q is negligible compared to h to p. So this whole expression cannot be given by this part because it's negligible. It must be given by this part. This is the dominant part, the part which creates h to p. And this tells me that when h is really, really small, I can afford to ignore this part because this one is really the majority of the number. It carries the weight. Here we go. Approximating sign zi minus yi. So it really does work out as if we just replaced the solution by this more precise solution, approximate solution, but there is actually a reason, a justification for it. And now we can use this EI in the same way that we would use this. For instance, we could look at maximum of absolute values, and that would be the global error estimate. So this is the competitor. We have two competing methods for estimating the error of our approximation. Let's try it out. So again, we start by this familiar differential equation which produces sort of like a periodic error. This is the error estimate for the Euler method. Again, step size is 0.5. Red curve is actual error. Blue curve is the estimate using control method. And it actually seems to work a little bit better, which is not the reason why we use it, because there are some problems from differential equations where the Richardson estimate works better. But here, yeah, here the control method actually produces better estimate. And if we try to go down with the step size to 0.1, we are getting almost a match, which is something that the Richardson didn't quite do. So this is very nice. Let's have a look at the local performance. Here, the red curve, that's the local error for different step sizes h at a specific place of that differential equation, of that solution. The green curve is the Richardson estimate, and the blue curve is the control method estimate. And you can see that for this local error, actually the Richardson works a little bit better because it's closer to the actual error. So as I said, these two methods are roughly comparable when it comes to quality. The difference lies elsewhere. Okay. In this graph, we can see both estimates at the same time, and this really confirms our feeling that the Richardson estimate is not as good as the control method estimate for this particular initial value problem. Let's try something more challenging. Do you remember this differential equation where the solution goes like that with a nice asymptote? And our higher order methods, they were just trying to float away, this stability problem that we had to cure by making step size small. Let's see how our error estimates actually handle exactly a situation like that. So I'm going to read the differential equation, and let's have a look at this code again. Here we go. Now, that's an interesting picture. What's happening here? Well, the red curve, that's the error of the Euler method. And if you remember the Euler method, it was quite sort of like not keeping up with the two bands, but then it followed the solution faithfully. So that was really good. That's why the error goes down. And the green error uses the Richardson estimate, which also uses the Euler method, which is also following the solution faithfully. So this is good. That's why the green curve actually follows nicely the red one. The blue curve, this one uses control method of order 2, but the control method runs away from the actual solution. And that's why if you use it to approximate the solution, you are making a big mistake. So there is a big difference. But if we pass to smaller step size, if we cure this instability, things should become much nicer. And they are. So as you can see, the three curves, the actual error, which is the red curve, the green Richardson estimate, and the blue control method estimate, they are all close together. So yeah, even for such a complicated situation, this still works okay. We have nice, workable error estimates, and the good question is what we can do with them. Let's have a look at it. A customer comes to you and asks for you to approximate solution to some initial value problem. So you choose a step, let's say based on some experience, and you develop, you create an approximation, and then you, let's say, use the control method or use the Richardson approach, and you also produce error estimate for the global error. And the customer looks at it and says, oh, wait a second, this is too much, because I have some epsilon tolerance which is permitted, and this is more. So what do? Well, normally you could try it by trial and error. So you take smaller step and smaller step and smaller step, and you are waiting for the error estimate to drop below epsilon. But there is a better way. What happens if you decide to modify the step by some constant s, typically between 0 and 1, but it could be more than 1 sometimes. We will get to it. What happens to the error? Well, the new error will be, let's call it ESH, according to the method of power of order p, which we have over here and over here. The new error will be s to power p times e, times the estimate that we had before. And customer wants us to have this less than, smaller than epsilon. That's a simple inequality that you can solve. And s should be taken smaller than epsilon over e, pth root. So you don't have to go by trial and error. You just generate one solution with a step size which you get from experience. Then using one of these two approaches, you estimate the global error. Compare it with the prescribed tolerance. And if your error is too large, you determine how to modify your step size, which means that in the next approximation, you most likely get the answer right. Very nice. We actually saw something like this when we are doing numerical integration. So this is very neat. But again, there is a special twist, because here we are dealing with differential equations, with functions, with approximations of functions. So there is something to the story which, let's say, is not completely perfect. Typically, when you are solving a differential equation, then the solution has different sections. Some sections are nice, and some sections are, let's say, difficult. And you pick a step size, you apply it, and you get an estimate for the global error, and you find that it's too large. So you have to use a smaller step size. But that means that you will have to use smaller step size everywhere, which is wasteful, because typically here you would have a larger error and here a smaller error. So it's much smarter to actually adapt the step size to the situation. Here we can use to our advantage that actually all the methods that we cover here are local. They are one-step methods. So we don't have to worry about a regular partition. We start with a specific step size, and we make one step, and we check on the error. And if it's good, we keep it. If the error is too large, we make the step smaller until we are happy. Then we make the next step, and again we check on the error, and the next step, and we check on the error. Now, if the error is too large, we make the step shorter. And if the error is too small, that's where it gets interesting, we can afford to make the step larger. So in sections where the solution is nice, we are really running ahead very quickly by big step sizes and cover it quickly. Then when the solution is difficult, we slow down and we make really tiny steps, real careful, we follow it. But then the solution becomes nice again, so we increase the step size and we go quickly to the end. So this is very efficient because it saves work. These are so-called adaptive methods. Methods where the step is a separate entity, it's actually a variable, which is changing step by step. How does it work? Well, you are sitting at some place, you make one step, and typically we use this approach, this control method approach. So we make one step with method of order P, one step with method of order Q, and we look at Zi minus Yi. Now the problem is that this is just one step. So this is actually a local error rather than global error. So we can expect this to be C times H2P plus 1 rather than just P. Now we could use this in this reasoning to isolate an alternative formula for S, for the scaling of the step size. But what people typically do is that they divide by H, and then they get expression which is of order P, and therefore they can apply this general approach, which is much more convenient. So this is actually something that we will shortly see, this expression, 1 over H Zi minus Yi, of course in absolute value. We are here asking about the magnitude of the error. So This allows one to solve even difficult differential equations rather efficiently because you are not wasting your time on sections which are quite okay. This brings us to the important question of work, because when it comes to small step sizes, you have to make really, really many steps, and this takes time. And time is precious. So where are we actually losing the time? And when we look at the algorithm for Runge-Kutta methods, the problem is not with those segments, because it's just addition, multiplication, very easy. Majority of calculations is spent on actually evaluating the right-hand side of your differential equation. When you're looking for slopes, every slope costs time. So how many slopes do you have to actually evaluate to make one step and get an error estimate for it? That's important. So let's have a look at the Richardson. You are sitting somewhere and you want to move using a method of order P. For a method of order P, for those yi's, you would need to find P slopes, K1 through Kp. But then you want to get the control data, you have to make two steps with the same method. To get to Z to I, you have to actually need P slopes again and again, because you are making two steps. So 2P slopes. Altogether, 3P. So that's how much work you have to do to get the Richardson estimate. 3P calculations of slope. Let's have a look here. We have a method for yi of order P, and for zi we have a method of order Q. For yi, you need slopes K1 through Kp. For zi, you need slopes K1 with tilde, let's say, through Kq. So altogether, you need P plus Q slopes. Now, typically, because you don't want to work more than you need to, Q will be just P plus 1. You have a method of specific order, and for the control, you just go up by 1. So typically, all you need is 2P plus 1 number of slopes. Now, if your method is of order 1, then you get 3 here and 3 here, and you don't have to worry. But typically, you are using a method of higher order, and then this is less work compared to the Richardson approach. So that's one of the reasons why you may actually skip Richardson approach, although it's really good. It works well, but it needs time to work out. So here we have a preference for the control method approach because it needs less work, but that's not all. Notice, here we need some slopes, and we are actually moving from one place to another. Here is xi, here is xi plus 1, and we want to move the solution. So we are looking ahead, looking for slopes at different locations. When we are developing the solution zi, we are actually looking, again, from point xi forward. We are sounding the situation like that. So the slopes k and the slopes k tilde, they are taken from the same range somewhere. And here is a key question. Could we somehow arrange that this control method actually uses the slopes of the real method, the one that we want to keep? That would be wonderful, because if these slopes are actually recycled, then we don't need 2P plus 1, we need just P plus 1 slopes. And that would be wonderful. Unfortunately, it doesn't work like that. When you look at typical methods, RK2, RK3, RK4, and so on, you will find that these slopes are actually taken at different places in a different way. It's not quite possible. However, there is a possibility, and one guy came up with it, to take RK4, which is our favorite general purpose method over here, and find a control method, RK5. But this is not RK4 as we know it, as we saw it before. It's tweaked. You change it a little bit. And this is definitely not easy, because you have to be careful when you are tweaking the method, because you don't want to lose the order. So there is a way to tweak RK4 and RK5 in such a way that they share majority of the slopes. So normally, when you have method RK4, RK5 as a control, you would need 9 slopes. That's the maximum. With a bit of luck, with extreme bit of luck, you would need 5 slopes. because you would recycle the 4 and you would add the 5th one. So 5 slopes, that's the ideal. But this ideal cannot be really achieved. What the guy did, he found a version which just needs 6 slopes, which is almost ideal. Definitely much better than 9. This is the 1/3 down. This is big savings, 1/3. So let's have a look at the method which combines 2 ideas. First of all, it very smartly uses modification of RK4 and RK5 to save on calculations of slope. And secondly, it uses this adaptive process of adjusting step size at each step. And this will be the most powerful method for today. Here we go. RKF45. RK for Runge-Kutta, 4 for the basic method, 5 for the control method. And F is Fulberg. That's the guy who actually invented how to merge those slopes, how to find common ground. So how many slopes do we see? Evaluate, evaluate, evaluate. We see 6 slopes. Where are they taken? Well, let's have a look at it. K6 is taken half the way, xi plus 1/2 h. K5 is taken all the way. You make the full step. But then K4, you take 12/13 of a step. Now, actually, I appreciate this. I really like 13, so I really appreciate that the guy managed to put 13 into the picture. So you are taking those slopes at all kinds of crazy locations. Now, after you find them, you go for yi. This should be method for the 4, so how many slopes are used? 1, 2, 3, 4. That fits. 5 slopes for the control method z. 1, 2, 3, 4, 5. That also fits. Which slopes are actually being used? Well, notice that we never use K2 when we are doing the final step. So the slope K2 is just auxiliary. It helps you to figure out the other slopes. That's interesting. Now, when you look at the coefficients, I mean, look at this. Fraction with 56,430 in the denominator. I have never seen a fraction like that in mathematics anywhere else. I mean, this must have taken an enormous amount of work to find such crazy coefficients. So this guy Fulberg definitely deserves the credit and deserves the right to be in the name of this method, because this was crazy. Anyway, notice that the step size h is actually not h, but hi. It's a specific step size for each step. And after we find the error over here, there's error estimate, we compare it with epsilon, and if it's too large, we find S, according to the formula that we can see over here. P is 4, so we take the 4th root, and we adjust and redo the calculations. And if you are happy with the error, we just keep going on with this H. So that's the RKF45 method, and it's supposed to be really powerful. Let's have a look at it. To make our life interesting, I'm going to return to this almost exponential example where the solution is bounded, and Runge-Kutta methods had tendency to run away if the step size was large, namely if the step size was 0.5. So let's have a look at it again. Blue squares, that's the Heun method, and it runs away. Crosses, that's the midpoint method, runs away. Circles, that's the RK4 method, runs away. And the black diamonds are right on the solution, that's RKF45. Very nice, follows the solution faithfully. Very good. So RKF does seem to work much better than the Runge-Kutta methods that we covered. It actually is the default method for Maple. Maple calls it high-quality numerical solution. So this is really a hardcore method. There is a but. But differential equations can be really nasty. So you can never feel totally safe. One has to be always careful. So let me now show you my favorite differential equation, which I call giant killer, because it can kill any numerical method. Let's make some room. Let me explain closely what's happening. Here we go. Y prime is equal to y minus sine of x plus cosine x. That's a very nice differential equation. No crazy formulas, no forbidden areas in the plane. Very nice. Initial condition y at 0 is 0. When you put it all together, the solution is the sine function. So there's nothing mischievous or devious about this differential equation. As a matter of fact, the next topic is linear differential equation, and I will tell you that they are the best type. This is a linear differential equation. So by any criteria you can think of, this is the very best differential equation. Let's see how the methods that we covered deal with it. Well, step 0.5, as usual. Here is the picture. These are the Runge-Kutta methods. So Runge-Kutta method of order 1, that's the red circles Euler method. And it didn't even go all the way to the first hill of the sine function. It's run away. Then there are blue squares, red crosses, that's the order 2 methods. Blue squares, that's the Heun method, red crosses, midpoint method. They lasted one hill, now they shoot up and they are gone. Black circles, RK4 method, our favorite. It goes around one period okay and then it runs away. Now perhaps this is the case of conditional stability. You have a differential equation, initial value problem, and the methods do not give you satisfactory results, so you go to a smaller step size and things are cured, perhaps, or perhaps not, we will see. So I'm going to change the step size to 0.1, and, well, the methods of order 2 lasted a little bit longer. Runge-Kutta 4 looks quite good, but at the end, it's a little bit wobbly, you know. I see a message that I don't like at the end. So I'm going to look a little bit farther along. I will increase the range of the picture twice. And indeed, RK4 runs away. What if I take step which is 10 times smaller? So I'm really, you know, working hard. This will take a while, probably. Yeah. Well, the methods are still running away. This time RK4 departed in the downward direction and goes to negative infinity. No matter what step size you try, how about 0.001? Well, perhaps, well, I don't want to be too greedy. Perhaps this is too greedy. Well, we will see. But you can try experiments like that at home, and you will try going lower and lower with the step size, and it will not help. For this differential equation, no matter what method you try, the solution will never be bounded. It will always go away from the actual solution. Really? How about RKF45? That's a good question. Let's go back to step 0.5, just to remind ourselves what's happening. We can see the circles, that's RK4 departing, and we can see little black diamonds, which look like they are threaded on the graph. They seem to be following the graph quite well. But at the end, again, it looks a little bit suspicious. So let's extend our viewpoint to the right. And we can see that also RKF45 departed. Now the trick is, you cannot somehow change the step size for RKF45 because it's an adaptive method. It determines the step by itself. What you can do, you can modify the epsilon, the specification of precision, and ask for a better precision. And if you do, then the solution will sort of follow the sine function for a little while, for longer, but then it departs anyway. So this differential equation, this initial value problem, actually defeats any numerical method. Why is it so? Good question. Here is the answer. 2-3 more lectures in future, we will learn how to solve this equation, how to find the general solution. And the general solution is sine of x plus c times e to x. That's the general solution. Now, as we know, all numerical methods are local that we cover here. So they don't really know what they are doing. They are sitting at a specific place, and they just try to follow the solution which is there. Now, sooner or later, this specific place will not be on the graph of sine of x. Why not? Because, well, every method has some errors, and moreover, there are numerical errors because we are running those methods on a computer. So what happens, sooner or later, your approximation is not on the sine function, but a little bit away. So the method decides to follow a solution, not the sine x, but the one which passes through this point, which is sine x plus some small constant times the exponential. Now, because the error was very small, let's say 10 to negative 9, there is not much difference. But already you are following not a sine function, but a sine function with a small number times exponential. The number is small, but the exponential grows really fast. So sooner or later, you run away with the exponential. If c is positive, you go up. If c is negative, you go down. And this is unavoidable. The moment you depart the sine function, you are later on gone to infinity. And this cannot be cured. Now, this doesn't sound all that optimistic, but it's actually not bad. It only shows that if we want to trust our answers, we have to have expertise and experience. And people who actually do real-life problems, they typically have both, so things are actually fairly okay. That's it for today's lecture. There is another sort of like a bonus lecture where I show two more interesting approaches to solving differential equations numerically. Two new ideas, and I think they're quite inspiring, so perhaps see you there. Yeah, I guess that's about it.